These normally take a lot of time just because there's a lot of steps to them. But the idea is, and like up here probably doesn't make a lot of sense right now. But when we get into problems, it'll make a lot more sense. The idea is what I was saying before is they're going to give you some equation that you're used to seeing, y double prime plus 3y prime plus 2 is equal to 5e to the 2t. So there's something that you're used to seeing, and they'll say, solve this equation using Laplace transforms. And the idea is you can take that equation, apply this stuff up here above the line, and by using that method, you can take that equation that has your t's, and you'll turn it into something that only has s's in it. So you'll have your function y and then s's. And when you have that, you can move it around a little bit. And the idea, when you have it in your Laplace form, you have it in your s's, is to get this capital Y of s by itself on the left-hand side.
So if you have to switch around, or am I reading it wrong? Do you want to eliminate all the s's and leave t's, or do you want to eliminate the t's?
This is to get the answer.
Oh, okay.
So then, yeah. Because once we move it to where we have y of s by itself on the left-hand side, then we want to get rid of all of our s's and go back to our t's, which is our final answer. Because this capital Y of s is the Laplace form of our final answer, y of t, that is going to be our answer to the differential equation that we're looking for. So if we can get this by itself, and then we do the inverse transforms to get it from our s's back to our t's, then we have our answer that satisfies the initial equation they gave us. And the cool thing is, if you notice, you plug in your initial conditions at the very beginning, so at the end you'll already have it. You don't have to solve for any c's or anything like that. So I'm going to go right into a problem and explain all this stuff in terms of that problem, because I think that's where it makes the most sense. What color do we want? Black, green, or blue?
Blue.
Blue. I don't have a yellow. I could if I write in blue then green, would it take the blue out and be yellow? We'll try that next time. I heard overwhelming blue, so we're gonna go blue. So I should probably get the paper that has a problem on it. So the problem that it gave was y double prime, y single prime. For most of the questions that I've seen for the full Laplace transform, they make it y single prime. It just saves a couple minutes, but it's very nice. So y single prime plus 5y is equal to 14e to the 2t. And it tells you that y of 0 is equal to 3. And it says, use Laplace transforms to solve this differential equation. So, looking at this, the first thing that we have to do is we have to take it from our t's into our s's. We need to transform it into the world of Laplace. And the way that we do that is we're going to use this stuff on the top right here. So we want to take the Laplace transform of this whole thing. So what that means is on the left side, we see we have a y prime. In order to take the transform, we're going to take that y prime, we're going to replace it with our s, capital Y of s, minus y initial. So we have s, capital Y of s, minus y initial. And the next thing that we have is a plus 5. Y, we replace that with capital Y of s. And that's equal to, now on the right side, we have some function f of t. And I'm just going to leave it right now as the Laplace of 14e to the 2t. We'll worry about actually taking that Laplace later, but for now, we want to get our capital Y of s alone on the left side. So now, let me explain a little bit more of where these come from. If you notice, whatever our derivative is, so when we have a y to the second derivative, we start off with an s squared, okay? Our first term always has our capital Y of s, and since we have a double derivative, or second derivative, we start with s squared. Then we work our way down by 1 power of s each time until we get to s to the 0, and that is our last term. So we have s squared times capital Y of s. Then, since that's squared, I need to have an s term. So I have an s term, and what I plug in with that is my initial condition for y. So y at 0, and then this was s to the first, I need to have an s to the 0. So I go one more where I have s to the 0, and what I multiply that by is the first derivative, so y prime of 0. And you can see that trend carries on with all of these. Yes?
They'll always tell you when to solve the Laplace transforms, right?
Yes. Yeah, they'll say solve this problem using Laplace transforms.
It's on the table, right? It's like s squared ys.
Yes. So these equations are on the table at the very bottom, properties of Laplace transforms. They're just written very differently. But if these three equations are the bottom three written on your table. So you don't have to memorize these, but understanding what these are because they look different in here helps. Okay, so does where we get these make sense and how we apply them to the problem make sense? I don't see any hands. So now we have to go get to this step. We want to get y of s alone by itself on the left-hand side. So what we have to do first is I'm going to plug in my initial condition, which is 3. So my y of 0, I'm just going to change out with 3. And since I want to get y of s by itself on the left, I'm going to add that over to the right side and get rid of it there. Next thing that I'm going to do is factor out a y of s, and that's going to be equal to s plus 5 is equal to the Laplace, very bad L, the Laplace of 14e to the 2t plus 3. Now, one thing that you can check yourself at this step, whatever you have, when you factor out your capital Y of s, whatever you have multiplied by it, so this s plus 5 should match the form of your auxiliary equation if you were to make it. So if you notice, right here, we have y prime plus 5. If I just ask you to solve for the homogeneous and write your auxiliary equation, you would have written m plus 5. This should always match that. It's not a coincidence. It will happen every time if you're doing it correctly. Even if you have an s squared, it would match your s squared plus 3s plus 5. So that's just a place you can check yourself in the intermediate steps. Then the last thing that we want to do is we want to get that y of s by itself. We just divide it over to this side. So we have s plus 5. And what we're left with is we have capital Y of s is equal to the Laplace of 14e to the 2t plus 3 over s plus 5. So now we achieved that first star that I have written over there. We got y of s by itself on the left-hand side. And I really want to move on to that last step where it says use the transform table to change this so that way all of my s's go to t's. The only problem is I haven't done that step yet. I haven't actually taken the Laplace of 14e to the 2t. So we can do that right now. So if I want to take the Laplace of 14e to the 2t, for that I can look at my transform table that they give me. And what it says on the table is if the one that we're looking at specifically is if we have something that's in the form of e to the at, that turns into 1 over s minus a. So in this case, I have a 14 out in front, which I can just keep out in front, and my a value is 2. So the Laplace of this is just going to be 14 over s minus 2. So I can take this and plug it in where I have my Laplace written up there. So we have 14 over s minus 2. So now I have all s's. I don't have any t's left, which is good. I have my y of s on the left side. So now I can use the transform table to change the equation so that way all the s's go to t's. But now I found another problem. I don't see anything on the table that looks like that. That looks really funky. So what do you think we're going to end up having to do in this problem that you tend to have to do a lot with Laplace? Partial fraction decomposition. Yes, we do. So the first thing that I'm going to do is, I don't like that I have a fraction over a fraction. It doesn't look nice. So what I'm going to do is I'm just going to do this divided by that and this divided by that. So it's going to turn into 14 over s minus 2 s plus 5 plus 3 over s plus 5. Now at this point, you have two options. The first option is you can get a common denominator, so that way you can add these two together and you'd have one fraction, do partial fraction decomposition, get your answer, and move on with your life. The other option that you can do is kind of take this 3 over s plus 5, because this I see is already in the form of something on the table I can do. So if I want, I can kind of ignore this for now. I can do partial fraction decomposition with just this, but then I have to remember to add in, I'm going to get some constant over s plus 5. I have to remember to add that back with this 3. So I prefer to just make it one fraction and then do partial fraction decomposition from there. Because that way I know that I don't have to remember anything at the end. I'm just focusing on everything that I have. So, I'm going to do a little board flip. And I have capital Y of s. In order to make them common denominators, I have to multiply my fraction with the 3 by s minus 2 on top and bottom. So we have, this is equal to 14 over s minus 2, s plus 5. This is going to be 3 times s minus 2 over s plus 5, s minus 2. So now they have the same denominator. I can add them together. So we have capital Y of s is equal to, this is going to be 14 plus 3s minus 6. So it's going to be 8 plus 3s over s minus 2, s plus 5. Now we have a single fraction. We can do some partial fraction decomposition. So we have a over s minus 2, and we have b over s plus 5. So now, I'll pause from this a little really quick. A couple things with partial fraction decomposition. Whatever we have in the denominator, in terms of our whatever power of s we have in the denominator, the power of s in the numerator needs to be 1 less. So here we have an s to the first, which means in the numerator we have s to the 0, which makes sense. But if I were to have a term where the denominator was s squared plus 3, my numerator has to be 1 power less, which means I have to have as plus b. Does that make sense? Is that something we remember learning, hopefully? Yes.
What if it's like s minus 2 squared?
So you're saying if we have, instead, we have s minus 2 squared as one of our factors. I'm glad you asked that, because the way that we handle that is, since the s is only to the first power, we still keep the a, but we have to account for the fact that there's 2 s minus 2's, so we add on a b over s minus 2. So if one of these factors is s minus 2 squared, it turns into both of these right here. It turns into the a over s minus 2 squared plus b over s minus 2. Does that make sense? Yes. Yep. So whatever the power of s is in the denominator of this right side, the power of s in the numerator has to be 1 less. So if one of my factors that I get, so if one of these was s squared plus 3, since I have an s to the second power, I know the numerator has to have an s to the first power. So I do a times s, but then similar to undetermined coefficients, I have to work my way down. So I do a times s plus b. And for some, if I had like an a times s squared, I would do b times s plus c. You work your way down covering each of the terms. Did I see a hand? Is that hand still up? I thought you raised your hand. Nope, sorry. Yes.
So in the case that there was the s minus 2 squared, you're saying you would keep s minus 2 squared and then you just add the, like, just like that? Like, it stays squared in one of the terms?
So these are two different situations. Here we have just our s's squared. Here the whole factor is squared.
Okay.
So if the whole factor is squared, then since my s is still to the first, I only need an a on top. But since this is squared, I have a second term where it's just to the first.
Okay, thank you.
That's added on. Any other questions? Cool. So now coming back to here, what's the next step in undetermined coefficient in the thing that we're doing? Partial fraction decomposition. Yes.
Multiply the bottom over it.
Yes. So we don't like fractions, so we're going to multiply everything by this denominator. When we multiply this left side by the denominator, it goes away because you'll have it in the top and on the bottom. When you multiply this term by the denominator, the s minus 2 term is going to cancel out. We're going to multiply it by s plus 5. And the b, we're going to multiply it by s minus 2. So what we're left with is 8 plus 3s is equal to as plus 5a plus bs minus 2b. And now, this step is the same exact thing that we did when we were solving undetermined coefficients. The left side has to equal the right side, so I look at all my terms with s's in them. On the left side, I have a 3. On the right side, I have an a plus b. Then I look at all my terms with constants, and I have an 8 is equal to 5a minus 2b. And when I solve that system, I don't feel like doing, yeah, I'll do it now. So when I solve this system, I know that I get a is equal to 3 minus b. And I take that, I plug it into down here. I have 8 is equal to 5 times 3 minus b minus 2b. So I have 8 is equal to 15 minus 5b minus 2b, so it's going to be minus 7b. Subtract 15 over, it's going to be minus 7 is equal to negative 7b, or b is equal to 1. Take that, bring it up here. That means a is equal to 2. I found both of those. I can plug it into what I initially had up here. So now I know my capital Y of s is equal to 2 over s minus 2 plus, not b, plus 1 over s plus 5. And now, finally, we have our capital Y of S on the left-hand side. And on the right side, we have something that we can use the table to transform from S's into T's. So I look at my transform table, and I see that if I have something, it's actually the same thing that we had up there, just going left now. We have something over S minus a number. So that means my A value is 2, and that will turn into, I'm bringing this 2 out in front. We have e to the at, where a is 2, so we have e to the 2t. Plus, in this case, my a is going to be -5, so I have e to the -5. And when I do from this step to this step, I'm taking the inverse Laplace transform because I'm going from S's to T's. When I take the inverse Laplace of capital Y of S, it just becomes Y of T. And this is my answer that satisfies the equation. So if I were to take that Y of T, take the derivatives, and plug it into that top equation that we started with, it would be equal. Yes. It should be a T, yes. Thank you. If anybody has any questions, let me know. You can come up and swipe up here. And shameless plug, if you guys are working on like planning out your schedules for next semester or working on your study plans, tomorrow, SigEp in the afternoon, we're having at our house like a study plan seminar. We're gonna have a bunch of older brothers from different majors that can help you out. Planning classes, picking out what semesters to take each class. If you're interested in that, I'm pretty sure it is from 1 to 3 tomorrow at our house. I'll send out details in the email that I send out after this. Otherwise, thank you very much for coming. I hope it helped. Good luck on the test. Have a good night.